Now it's time to return back to rotations. So we remember that we had two different types of variables. We had translational variables, and we had angular variables. So in terms of translational variables, we had position, we had velocity, which was the change in position with respect to time. We had acceleration, which was the second derivative of position with respect to time. And we had kinetic energy, which was 1/2 the mass times the velocity squared. Now in terms of angular variables, we had the angle theta, and I write it with a vector because there's really, if you remember, there's really two ways that we can write an angle. Right? We can call theta going in this direction, and then you would say minus theta. This would be like an angle of minus theta, would be going clockwise. So similarly, we have omega, which was a change in the angle with respect to time. This was also, we call this the angular velocity. And then we had the angular acceleration alpha, which was the second derivative of the angle with respect to time. So this was telling us if our angular velocity was speeding up or slowing down. And we even had a kinetic energy that was rotational, that was 1/2 I omega squared. So we also had this this quantity I that we said behaves like mass. But now think about what we used in our analogy for the moment of inertia. We said momentum, and we said that mass in this case is really telling us how much something resists having its momentum changed. So in other words, we had this quantity momentum, which is mass times velocity, and the mass is telling us how hard it is to change that momentum, because because we saw one of the fundamental laws of physics is that momentum is conserved, and so something would have to actually change our momentum, and our mass is telling us how hard it is to do that. Now, there's something similar in the case of angular variables. We said that the real definition of the moment of inertia, is how much something resists having its angular momentum changed. And so as you can imagine, angular momentum, which we call L, is I times omega. I, our variable that acts like mass, telling us how much something resists having its rotation changed, and omega, the variable that represents our rotation, how fast something's spinning. And so this brings us to another new concept, and this again is another fundamental law of physics. Okay, something that's spinning, if we put it out in space, is going to remain spinning with the same angular rotation, this same angular momentum, I times omega, unless there's something that acts on it, unless we have a torque or a force applied to it. And so to show how angular momentum works, we can take a look at this figure skating clip. Okay, and so we notice that. So notice the skater; she has her arms out more, and we learned in the previous section in rotation that the further away you are from the center of mass, the larger the moment of inertia. So what this tells us, just by looking at our equations, is that if we have a larger moment of inertia, we're going to have a smaller angular velocity. Whereas if our moment of inertia gets smaller, all of a sudden our angular velocity is going to increase. So what we would expect, let's pause it for a second. So pause it for a second and think about what you would expect if she brings her arms in. Okay, so now let's see if you were right. So here she is spinning. Now she brings her legs in, now she brings her arms in, and you can see that she's spinning much faster. And why is she spinning faster? Well, because angular momentum is conserved. And since angular momentum is conserved, that means that if the moment of inertia goes down, the angular velocity goes up. If the moment of inertia goes up, the angular velocity goes down. And that's all there really is to it.